This PowerPoint presentation is from section 14.7 of our OpenStax textbook and will introduce important concepts about acid-base titrations. A titration is a way to perform a reaction such that you can add one reactant to another until the reaction is complete. Titrations are usually performed using a burette to deliver a precisely known volume of a solution that is called the titrant. That's titrant with a T. In an acid-base titration, the solution in the burette can be the acid component or the base component of the reaction. If you know the concentration of the titrant solution, you can easily determine the number of moles of the titrant reagent that have been added to the reaction using the formula moles is equal to the molarity times the volume. Titrant solution is added until the equivalence point of the reaction is reached. The equivalence point is the point at which the moles of added titrant will stoichiometrically react with the moles of reagent in the receiving vessel. Typically, an Erlenmeyer flask is used as the receiving vessel. The solution in this flask contains the other reaction component. The solution is called the titrand with a D. An important point about titrations is that they always involve a chemical reaction. The burette is used to deliver one of the reactants to the Erlenmeyer flask that contains the other reactant. This setup allows you to add just the right amount of reactant in the burette to exactly react with the component that's in the Erlenmeyer. How will we know when we've reached the equivalence point? How will we know when to stop adding reactant with the burette? We need some way to visualize this special point. Many titrations are performed using a special chemical called an indicator. These chemicals have different colors in different pH environments. As we'll see in a little bit, use of these indicators will provide a visual signal about when to stop the titration. We have to make a small distinction here between the equivalence point of the titration, which is a somewhat theoretical point at which the exact amounts of the two reactants have been added, and what's called the end point of the titration, which is when we actually stop the titration due to an observable change. You've probably performed titrations in your first semester general chemistry class. Let's look at a simple example. What is the molarity of a diprotic acid solution if it took 26.35 milliliters of a 0.1 molar sodium hydroxide solution to neutralize 20 milliliters of the acid solution? Titration problems always start by writing down the titration reaction. In this case, we have the reaction of our unknown diprotic acid, H2A, with the sodium hydroxide reagent. Since we have a diprotic acid, it will require 2 moles of sodium hydroxide for the complete reaction or the complete neutralization of our acid. The products of an acid-base reaction are always water plus the salt of the acid. To balance this, we'll need to have 2 water molecules formed because we had 2 hydroxide and 2 H pluses. This is our balanced titration reaction. To solve this problem, let's start by writing down the given information. In terms of the sodium hydroxide, we're adding 26.35 milliliters of that. And this solution has a concentration of 1 molar. 0.1 molar. In terms of the acid, we know that we're neutralizing solution that is 20 milliliters. So we first want to find out how many moles of sodium hydroxide we're actually adding. Recall that molarity is given as moles over volume, so we can rearrange this to solve for moles as molarity times volume. So we have 0.1 molar sodium hydroxide and we're adding 0.02635 liters of this solution. Notice I did the conversion between liters and milliliters. So that gives us 0.002635 moles of sodium hydroxide that we're adding. We also know that there's a 1:2 ratio between the amount of sodium hydroxide we add and the amount of acid that was in our solution. So let's take our amount of sodium hydroxide and figure out how many moles of acid must have reacted using our 1:2 ratio. This calculation tells us, that we must have reacted 1.3175 times 10 to the minus 3 moles of the diprotic acid. What we actually wanted to calculate was the molarity of that acid solution. The molarity of the acid solution is going to be the moles of acid, which we just calculated, divided by the liters of the H2A solution. "20 milliliters in terms of liters is 0.020. And when we do the math on that, we get that our concentration was 0.0659. Actually 0.6588 molar of our H2A. Notice that we used the original volume of the acid solution, the 20 milliliters, because we wanted to know the original concentration of the acid solution, not its concentration at the end of the titration. Actually, at the end of the titration, the concentration of acid should be 0 because all of it has been neutralized with the added base. What new aspects of titration are we going to cover in this class? In Chem 51, we will be measuring and calculating pH values during the whole titration, not just what happens at the equivalence point. We'll also learn how to use the data from a titration to not only identify the equivalence point of the reaction, but also to determine the pKa or pKb if we're titrating a weak acid or a weak base. An example of something called a pH titration curve is shown to the right. The pH is usually plotted on the y-axis, and the volume of the added titrant is plotted on the x-axis. Titration curves typically have the special S sort of shape, and we'll see more about this in later slides. Let's review some key concepts. Titration is a method of volumetric analysis. The equivalence point of the titration is defined as the point when the moles of titrant added stoichiometrically equal the moles of the other reactant present. The endpoint, on the other hand, is when the titration is typically stopped due to a change in indicator color. pH calculations for titrations will use procedures that we've already learned. If we're dealing with a strong acid, strong base titration, we will just use stoichiometry. However, if our titration involves a weak acid or a weak base, we'll need to use equilibrium concentrations as well. When we do a calculation or a titration of a weak acid or a weak base, we'll find that the shape of the pH curve changes a little bit. The weaker the acid or the base, the shorter and less steep the change in pH at the equivalence point will be, making titrations of very weak acids or bases more difficult and less accurate. What are some problem-solving strategies for titrations? These are similar to strategies that we've discussed before. When given a problem, you want to make sure that you identify the major species involved and look for possible reactions. Do the stoichiometry reactions first. These are the reactions involving a strong acid or a strong base, the ones that go essentially to completion. If after taking care of those, you still have acids and bases in your system, you'll want to deal with any equilibria issues. Another point to remember is that the volume is constantly changing during a titration, so you'll usually want to do your calculations in moles and then solve for concentrations by considering the new total volume. In this video presentation, we've covered some basic concepts about acid-base titrations. You should now be ready to work on problem number 16 from the group work packet that asks you to calculate the pH values during a strong acid, strong base titration and plot the theoretical titration curve. After practicing these calculations, we'll move on to calculating the pH titration curve for a weak acid, strong base, and we'll do that in a second video called Part 2.